Trees are an important data abstraction for representing hierarchical relationships. We've drawn pictures of trees before and discussed how in computer science they grow upside down. Now we'll talk about the common vocabulary used to describe trees. There are in fact two different metaphors used regularly. The first is the recursive description of trees, where a tree is like a wooden tree, like an apple tree. In this description, a tree has a root label and a list of branches. There's the root label, there's a branch. There are only two branches to this tree, and the other branch is here to the right. By the way, each branch is a tree. That means the branch has a root label as well. A tree with 0 branches is called a leaf. So there's a leaf with no branches. It does have a root label of its own. Now, once you've constructed a tree recursively, you might want to describe certain locations within the tree. And so we say in the relative description about family trees that each location in a tree is called a node. So here are all the nodes. I've circled them. And this is the root or the root node at the top. Each node has a label that can be any value. So the data stored within the tree are stored at the labels. Now, the reason I call this a family tree relative description is that one node can be the parent or child of another. So we can say that this node containing 2 is the child of that root node containing 3. And you can also describe other familial relationships, such as ancestors and descendants and siblings. By the way, people often refer to the label values themselves by their locations. So something like each parent is the sum of its children, which is true of a Fibonacci tree. Now that we can talk about trees, we can talk about implementing the tree abstraction. A tree has a root label and a list of branches, and the constructor is going to take those 2 values. Each branch must be a tree. So if I want to construct a representation for this small tree, I would write the following code. It's a tree where the root label is 3, and the branches are a tree with 1 and a tree with a 2, 1, 1. In this case, I'm using the constructor as I've described it, so that I can change representations however I wish. Now you might say, aren't I violating an abstraction barrier because I'm using a list? No, it's part of the abstraction that a tree has a list of branches. So it's totally fine that I'm using a list here, because that's part of the abstraction. It's not part of the representation. Now let's come up with a representation. I could come up with anything I want, and that will determine what actually gets printed out by Python when I evaluate this constructor expression. Here's what we'll get. It's just some lists within lists with the label values embedded within them. The way we construct this is to define a constructor tree, which takes a label and a list of branches. By default, the list of branches is empty. So by default, I'll get a leaf, which is why I'm able to call just tree on 1 in order to construct this leaf node here. I put the label into a list. Branches is already a list, and so I sum them together. The label of a tree is a selector that returns the element at index 0 in the list representation of the tree. And the branches are the rest of the list elements as a list. Now, in order to make sure that while I'm using the tree constructor, I don't build something that's not a tree, I'm going to add some checks. The first check here says for branch and branches, assert that the branch is a tree. That's part of the abstraction, and my code is going to make sure that I obey that abstraction as I construct the tree. I'm also going to call list on branches instead of just saying label in a list plus branches, in order to make sure that if I pass in some other kind of sequence, it gets converted to a list before adding to another list. So these two lines are really just there to verify that the tree definition is being respected within the body of whatever program I write. How do we know if a branch is a tree? Well, for anything to be a tree, it has to be a list. It has to have at least one element for the label. So if that's not true, we'll return false. And it has to be the case that all the branches are trees. So in fact, isTree is a tree recursive function itself that goes through every branch in the branches of the tree. If it's not a tree, that branch, then the whole thing can't possibly be a tree. If these two checks pass, then it must be a tree, because it has a label and it has branches that are trees. Finally, I'll add one more function to my tree abstraction, which is a check to see if a tree is in fact just a leaf, which checks that the branches are empty. If I call branches on tree and get back an empty list, that's a false value, so not branches tree will be a true value, just as long as this tree has no branches. Now that we have the code for our data abstraction, we can use it. We can create a tree that's just a leaf. Is it a leaf? Oh yes, it is. If I want to create a tree with branches, then I specify those branches in a list, because every tree should have a list of branches, which by default is empty. Now, if I just put a single value in here, I'm going to get an error that says branches must be trees. It must be the case that when I construct this, everything I put in the branches list is itself a tree. If I want a tree with branches to be one of my branches, then I give branches to that tree. And in this case, we'll just put a leaf. So I finished the tree rooted at 5. I want another branch, which is a single leaf, rooted by 6. Now I've listed all the branches for the tree, and there's the tree. Notice that when I evaluated this constructor expression, there were no errors because I've built a well-formed tree. Now it happens to be that it has this complicated nested representation, but that's not how I will access it. Instead, I'll just ask, what's the label of T? It's 1. What's the branches of T? Well, a bunch of trees. If I want to get the branch at index 0, then I just write that. That's a tree. And I can get the root label of that branch just by asking for the label of the index 0 branch. By treating branches as a list, I'm not violating any abstraction barrier because I said in my abstraction that a tree has a list of branches.